Good afternoon, everyone. Thank you so much for joining us. My name is Milad Ruhi. I'm an assistant professor at Durham School of Architectural Engineering and Construction at University of Nebraska. Also, I'm a current chair of ASCE EMI Objective Resilience Committee. I would like to welcome those of you joining us here in Omaha at PKI, and also our students and colleagues based in Lincoln. And also, I really appreciate, I see more than 100 participants online. Thanks so much for joining us. I would say this reflects the importance of resilience in our field. And we are especially excited to host this Objective Resilience Committee series with the great support that we received from ASCE and also Durham School of Architectural Engineering and Construction. We really appreciate the support and for this visit. So I'm going to have a quick note on the logistics. So the presentation going to run until about 1 p.m. for about 45 minutes. And we're going to reserve some time at the end for Q&A. So for those of you on Zoom, please feel free to submit your questions on Q&A. So we are going to make sure we are going to moderate the questions. But for those of you here in Omaha, please feel free to ask your questions. And with this, it's a truly a pleasure for me to introduce our speaker, Professor Alipour from Iowa State University. Dr. Alipour is a full professor and also Thomas Murray Faculty Fellow in the Department of Civil Construction and Environmental Engineering, ISU. Her research centers on the resilience of civil infrastructure systems, integrating probabilistic modeling and decision-making frameworks to assess and improve performance under multi-hazard conditions. Her work bridges component and system-level analysis, advancing strategies for more robust, adaptive, and sustainable building work. Dr. Alipour has authored over 150 scholarly publications, including articles in leading journals, conference proceedings, book chapters, and technical reports. Her research is supported by major U.S. funding agencies, including NSF, National Institute of Standards and Technology, National Cooperative Five-Year Research Program, NCHRT, and Federal Highway Administration, as well as enumerated funding from state and local agencies. Her contributions to research, education, and professional service have been widely recognized. She's the recipient of NSF Career Award in 2018, a senior fellow at ETH Zurich, and also she has received a number of honors from ISU, including ISU Interdisciplinary Research Team Award, Outstanding Engineering Faculty Award, ASC Iowa Section Outstanding Civil Engineering Award, and the College of Engineering Research Award recently in 2025. Professor Alipour is a fellow of ASCE and also its SEI, Structural Engineering Institute. So with this, please join me in welcoming Dr. Alipour.
Thank you, Dr. Ruhi, for the generous introduction, and thank you for the Durham School for supporting this event and inviting me here. I've had the opportunity to meet with the faculty and staff and visited some of the facilities on the grounds and have been very impressed with what I have seen in this school. It's a very interesting setup to have the two schools in Omaha and also in Lincoln. So that's very appreciate the opportunity. I would like to also thank the ASC Engineering Mechanics Institute Objective Resilience Committee for inviting me to this to give this lecture. I'm certainly both humbled and honored with this opportunity as I'm continuing the lineup of some of the leading colleagues within the field of objective resilience. So today, I'm going to present some of the ongoing work and some of the completed work in my research group at Iowa State University on the resilience of power systems under extreme wind events. I will highlight some of the emerging topics and some of the future opportunities that is there. And I hope that that opens up some opportunities for discussions and provoke some thoughts in the process. So we all, I think, we recognize the impact that natural hazards has on built environment. I always like to start with this graph that National Oceanic Atmospheric Agency produces on the natural hazards and also their impact on the building environment in U.S. Across nationwide and over the past four decades, basically. And what you can see here is that we can see an increasing trend of frequency of the events over the past 4 decades, and also the impact associated with them. The size of the bubbles are the cost in $1 billion and the impact on the community in the US. And one might say, a portion of this obviously attributed to the effects of increasing intensity and frequency of these events, which is true. But also the fact, for example, in the case of hurricanes, is because of population growth and urbanization that is happening in some of the prone to hazard regions, such as coastal areas where more people are kind of investing and moving into those directions. So what really this highlights is that the hazard has been there and it's going to continue to be there. And it's going to impact our communities. And to be able to address the impact of it, just looking into the structures and vulnerability of structures probably won't cut it. We would like to also look into the role that the vulnerability of individual components of the built environment has on the systems that they're part of, and eventually the communities that they serve. So for a specific, as I mentioned in this presentation, I'm going to focus on a specific part of the built environment, and that is the power grid line. And I'm going to specifically look into the high voltage transmission lines and their performance under wind events. So looking into just power grid lines, another graph, very informative, shows that we are seeing increasing vulnerability within our overhead grid lines and also transmission lines to these natural hazards. If you look into 2024 only, you will see that the electricity outages because of major events was at average of 11 hours per customer. This is about twice what it was in the past decade before that. And during this time, you can see that the planned outages have been kept similar, thanks to some of the federal regulations that is out there to ensure reliability of the system at about average of 2 hours. If we dig down a little bit deeper, just to look into 2024, we're going to see that right there in the middle is where we have the US average. And but some of the outliers are, for example, South Carolina, and we know what happened in South Carolina in 2024. We had downfall of Hurricane Helene, and together with that was other states such as North Carolina and also Florida that dealt with major wind and also storm surge impacting both transmission distribution and also substations and causing these large outages. So we can see that the vulnerability is out there. Now, while a substantial body of knowledge has been devoted to resilience of power grids within the power groups, power industry, we see that there's a disconnect between the vulnerability that is to physical components of power lines and also the resiliency of power grids. So there's a gap within research to connect these two. However, on the other side, when we look into the damages that we see after events, we see that a lot of that is stemming from damage and vulnerability of our physical built environment. And examples of that are shown. For example, the 2024 event of Illinois was not actually that big of an event, but the wind gusts were high enough to cause damage to transmission lines. In 2020, we had a derecho in Midwest. In 2024, we had major derecho and also tornadic events in Houston. We even have had damages because of winds to our power grids in California, right? So all of that highlights the need to kind of characterize this linkage that is there between the physical components of the power grid line and also the operationality and resilience of that. I always also like to show this example because it hits close to home, right? This is an example of the August 10, 2020 derecho, which resulted in gusts up to 140 miles per hour, sustained winds of more than 67 miles per hour that lasted for close to 1 hour, which is very unique for itself, and caused damages in 5 different states. Just by a show of hand, any of you experienced that or heard about the derecho in Nebraska? All right, okay. So it hit really close to home. At the time, we were working on this topic. I had started working on this topic thanks to funding from National Science Foundation, and we clearly could see that this damages to the physical environment is elongating the restoration time and also outage times for our communities. And one of the things that I did at the time, I reached out to multiple utilities, both municipal, cooperative, and also investor-owned across Iowa and also some of the neighboring states, and had discussions with them as to what went wrong in terms of restoration, what they thought that was needed in terms of kind of addressing and preparing for an event of this scale if it would happen again. And one of the common points of response that came up was the lack of a resilience planning tool. And that kind of initiated us into development of and kind of gearing our research and studies towards development of resilience assessment tools that would help utilities start planning for this type of extreme tail events in future. So I've been talking about resilience a lot. And I would like to go over this famous resilience curve for a minute to kind of discuss what we will be looking at in this talk today. Resilience is normally defined as, we normally define as some sort of a system functionality measured in some metric. And that obviously is dependent on the type of decisions one needs to make or type of infrastructure they're dealing with, and also a scale of time. We have an ex ante phase and an ex post phase, and decisions on the ex ante phase impact the ex post phase immensely. While the infrastructure owner can start planning for mitigation events, asset hardening in pre-event, and that would majorly impact how the functionality of the system would be diminishing after the event happens. Now, many of the studies that kind of dab themselves as resilience studies stop at this point. But really what resilience is the temporal evolution that happens after the event happens. How do we go about responding to the event and restoring the system to either its original condition or even better, to a better condition? And all of that is really impacted by a few things. Obviously, pre-event mitigation and asset hardening that we might have implemented in the system, but also pre-positioning, for example, restoration crews, resources, so that if failure happens, we can respond to it correctly, or even designing our network in such a way that it can self-heal in some words. And that is going to impact with what kind of slope you're going to be able to restore the functionality of the system. One of the major things that we discuss about is that the failures within a system are not avoidable. They're going to happen. But one of the things is that when they happen, they provide a window of opportunity. And that window of opportunity is kind of really dependent on how we plan before that. We know that there is some sort of a vulnerability within the system, but at the time, we do not have the resources to fix it. If it fails, if we have the plans in place, we can potentially restore the system to a better state and actually end up with a better system as well. So one of the things that I want to highlight here is that really restoration is very important. And I'm bringing some example here from historical outages that happened in 2 utilities that are very closely located, are managed by different structure. And we looked into their outages and their historical outages, and we made sure that we are looking into same size of outages, and kind of graphed it here and developed a mean graph and standard deviation of it. And you can clearly see that one utility is more resilient than the other one. utility, first of all, under the same events, because as I mentioned, these two utilities are closely co-located. So they're particularly impacted by the similar type of events, wind events. And obviously, utility 2 has much more outages under similar events. But at the same time, utility 1 is able to restore some of its functionality right away after the impact happens. And that's really because of the fact that this utility has implemented potentially microgrids, reclosers, potential backfeed opportunities so that we can get the power back on quickly. We also see that there is a very steep slope of restoration happening in the utility 1. And the reason for that is that they just did a very good job of assigning the resources to the locations that were the most critical so that they could reload the most critical branches of their lines. So our goal is really to be able to provide utilities with tools like this in a simulation space in such a way that they can see where they're standing, what could go wrong with their system, and how they can go about restoring that based on the system they have. And with that, I'm going to define my resilience framework here. So this is, I would say this is applicable almost to any other type of infrastructure system, and it's also hazard agnostic. Okay, so I'm going to implement it on a high voltage transmission line in the context of wind, but really you can put a transportation system and flood, and it would work the same way if you follow the rules of the network that you're working with. So the first step is really understanding the features of the network. How is it topographically distributed? What components are under? In the case of your transmission line, you want the location of the generation of the loads, you want the location of the buses and whatnot, even location of your towers, if you have access to it, what is the span of these towers, and any features of the physical components that would make it potentially vulnerable to the hazard that we are studying, in this case, wind. We also need to have a very good understanding of the hazard in the region and what are the probabilities of occurrence of those hazards, the intensity, frequency, distribution of the hazard geographically, because we're working with a geographic network. And then we want to be able to kind of layer these two in such a way that we can find exposure measures and understand what each component is exposed to in terms of intensity of the hazard. In this case, we will talk about this. Some of the important factors are obviously the wind speed, but also wind direction at the location of the assets. After that, after exposure is identified, we are looking into assessing the vulnerability of the components of the system. These are physical components of the system, parts of built environment that we always see. And potentially in the case of wind, they're overhead, so they're vulnerable to the wind. And we developed basically vulnerability functions for them to assess what is the likelihood of their failure. In this case, as we talk about the transmission lines, we're going to talk about something associated with the physical cascading in the transmission lines, but that's something probably more specific to the transmission lines as we talk about it. After that, obviously, this is a network system. There's a flow of material, if you could call it. There's some sort of a flow, in this case, power flow within the network that needs to be simulated. We're going to follow well-established power flow models. So we're not going to do any invention in that arena, but we're going to be very good users of it and be true to the basics of and the fundamentals of the model. And based on that, we can see the impact to the community. And based on the simulations that we do, we can come up with a plan for restoration, which is what really defines the resilience in this sense. So this figure basically shows the transmission network that we're working with. This transmission network is located in northeast of US, covers over about 6 different states. and includes about 39 buses. From a modeling perspective, what is important here is not just the geography, but the flow structure of this, which is established by the power models. And also, in general, when we look into the resilience assessment, we're looking into, obviously, topology, in this case of transmission lines, electric flow, power flow, and also the component attributes, which is, in this case, is going to be our transmission towers, conductors, and whatnot, and the length of the spans of, for example, transmission towers, assessment of the exposure, and so on and so forth. So going to the next level of our framework, we would like to have an understanding of the hazard, and we're not looking in the context of resilience assessment or analysis. We're not looking into a single hazard. We're looking to a distribution of possible events that could happen. So in this slide on the left side, what you're seeing is about 10,000 simulated hurricanes tracks that cross the North Atlantic Basin in this region. We generated them using the well-known storm model by Blumenthal et al. And the tracks basically capture the full variability of storm genesis, movement, and also intensity. From this larger ensemble, we develop about 1,000 realizations that kind of impact our study area, our study network. And based on that, basically we move from a single hazard analysis to a probabilistic hazard analysis that considers the potential variability that this system could be exposed to as it is placed in this location. So, again, what is important here is that as hazard is uncertain, and with this type of modeling, we are trying to capture that uncertainty within that. So now that we have modeled these hurricanes, a couple of things that we want to do is kind of looking into the statistical characteristics of those wind field realizations across all the storms that we have, capturing not only just the intensity, but also how the network interacts, so how the winds interact with the network. So on the left side in the wind speed distribution case, we are looking at the distribution of maximum wind speeds. And we can see that most of the events are clustering around a moderate intensity, but there's also some tail definition in the extreme cases that would be important for resilience events. On the bottom left, we are looking into the track persistence. Basically, we're looking into the number of retained track points that you can see it varies widely. And it basically shows how long the system is exposed to storm conditions. And you can see some of the storms pass very quickly, some of them sustained, and that sustainment really results in failure. So that's another aspect. And then on the right plot, we're looking into intensity versus the footprint, and it links the peak intensity to spatial impact, showing how stronger storms tend to affect a larger fraction of the network. But again, there is significant variability within that. So the idea is that not all the storms are going to be very damaging. Some of them are less damaging than the others. Some of them are going to sustain more within the network than the others. And all of that taken together show that hazard is very multidimensional, it's very probabilistic, and that needs to be accounted for. So now we move from statistics to space. So showing that those realizations actually, how they actually look when they're mapped on a network. And these are some sample realizations out of those more than 1,000 realizations that we had within the system. Each panel just presents one of those realizations, sample realizations, and the colors are basically showing how much exposure it has into wind speed. Within this data, we also extract the direction of wind with respect to the line of towers. That's not necessarily shown here, but that's something that is included within the analysis. So across this realization, what we are interested in is which components are exposed, how many components are exposed, and also the intensity distribution at the location of those components, and also the direction of the wind at those components. But all of these information is going to be entered to the next level, which is basically implementing the wind loads on our towers. So here we're going to go a little bit deeper into what happens within the structural system. Okay. Now we developed one of the major questions as we were addressing the transmission line vulnerability was what is the impact of the system nature of this? What is the interaction between conductors and towers? And there is certainly an interaction. And because of the dynamic nature of loading of wind on these systems, this interaction is dynamic and it's kind of random in a sense. So to be able to characterize that because of the lack of availability of information in this, we developed this pretty large scale elastic model of transmission line, 3 towers, 4 spans, 2 side frames. And the towers were modeled at 1/50 scale. Conductors were modeled at a skewed the scale factor of 1/200. And this test took place in NSF's wall of wind experimental facility at Florida International University. And a couple of things that happened was obviously as we were scaling, we had to make sure that this scaling is not only geometric, but also dynamic. So the dynamic characteristics of the system was preserved as the scaling down through simulated methods took place. For that, we made sure, for example, our towers are made of kind of aluminum rods that their stiffness represent the scaled down stiffness of the actual towers. To represent the aerodynamics of the towers, we used 3D printed cladding to show the shape of the components of the towers. Our conductors, we used foams on our conductors to represent the aerodynamic shape of the conductors. We had load cells at the base of the towers. We had accelerometers at the location of the cross arm of the tower, so it could measure the dynamic effects that is being transferred from the conductors to the cross arms. We also had strain gauges at the base of the columns to kind of again double check kind of our forces that are being transferred. And here are some basically summary of the type of things that we observed. We looked into the acceleration. Top 6 figures are showing the RMS of acceleration as a function of wind direction, the 3 towers that we have. And in the top row, you can see that Tower 1 shows the highest response, especially in the X direction, up to even close to 46% more than Tower 2, for example. And then the Y direction shows the largest overall values across them, peaking around 45 degrees. And in Z direction, Tower 3 shows growing response with a skewed wind. The bottom row compares the windward and leeward, the shear values, basically. We have shear in X and Y, and then we use that equation right there to kind of represent the shear values that you're seeing here. And as the plots show, Tower 3 consistently experiences the highest mean shear, especially under kind of oblique type wind events. And application effects are strong at 45 degrees. And so that's, so as you can see, different towers, depending on whether they are leeward or windward, whether they're first or last in the lineup of the columns with respect to the direction of the wind, have different responses. And so that's something that is not necessarily observed within a single tower design, but when a system of design is conducted, that is more observable. A similar thing, we looked into the more overturning moments. We can see that there are clear amplification at downstream towers, where Tower 3 has the most highest values. Again, in the MY direction at Tower 3, we have a strong sensitivity to wind direction, and especially when we have skewed flows, higher skew flows. And so with that, we took that, and one of the lessons that we learned from it, normally what we use within the industry is that we use the ASC's manual of practice to be able to characterize the loads on this, and understanding that, for example, the shear forces are different from one tower to the other one, depending on whether it's windward or leeward. We developed a kind of a amendment to one of the equations to ASC's manual of practice that is used for design. Now, how do we use that in real world? Is that in an ideal situation, if you have a model, a numerical model, which we're going to build it in a minute, we're going to be able to use these factors that are more realistically representative of the actual loads that are representative of interaction of the tower and conductor on the system. So moving on from this, we want to really build a numerical model of the towers, because that's what we really need to be able to input into our network models and go on from that there. So what we did here, we had one of our colleagues from Bonneville Power Association shared with us the test of failure data for a transmission tower. And first we built a numerical model of that in both ANSYS and OpenSys. And we validated the model of the tower itself with this. We developed talking about directionality effects, and just learning from experiments, the direction is very important in the loads that you're seeing. So we developed directional capacity curves for our tower. And then we developed this stochastic model for the wind loads on the both tower and conductors. Now I'm showing a portion of this system, but our system actually consists of multiple towers, so we can really see that dynamic interaction in our numerical analysis as well. But the idea is that we have the loads on both tower and the conductor. And so we also characterized the potential coherence that we have both vertically and horizontally within our wind loading through different methods that is available. And this is some major work that one of my previous students, Saransh Dikshit, completed there. Now, after we have completed the characterization of the loads, we want to be able to apply the wind loads and wind simulations. We want to apply this on the structure. And for this, we really need aerodynamic coefficients of the structure. But one of the aspects of this was that obviously this tower is changing over its height in the size and the exposure surface that it has to wind. And that's going to change the aerodynamic coefficients for different portions of the tower. So considering only one aerodynamic coefficient might be either conservative or non-conservative in a sense. So we did an experiment within our wind tunnel test to just characterize the aerodynamic coefficients for different portions of this tower that are more similar in a sense of more uniform in terms of the shape. And we used that for our analysis. One of our colleagues also did develop some empirical formulations for coefficient aerodynamic coefficients in conductors. We use that to be again more close to reality. And we use all of this information to be able to analyze our towers under these stochastic winds that are capturing the coherence in both vertical and horizontal directions, and in a very realistic, with a very realistic understanding of aerodynamic coefficients of these towers. And based on that, we came up with fragility functions. We considered, and this is another work again from Saransh, we considered different limit states within different components of the transmission tower. It is within the tower, within conductors, and within insulators. And based on that, we were able also to develop the fragility curves for the transmission tower system. And so now that we have this, you have to note that these fragility functions are a function of not only wind speed, obviously, but also different angles of attack. So the directionality of the wind with respect to the system is considered within development of this, which means if you remember, originally we had these realizations that had wind speeds and directions. Now they can read from these fragility functions as a database and kind of use to that. Now, a little bit irrelevant but interesting to this topic, we are also, my group has been working a lot on multi-hazard considerations for many types of structures, but also for transmission lines. And in this case, we looked into consideration of wind and ice, because freezing ice, ice and wind, all of that are important factors and have caused major failures, especially in colder regions that we have. Here what we did, we basically developed a framework that would capture the potential failure likelihoods under wind and ice. The idea is that when icing happens in a very approximated way of thinking about it, the weight of the ice is obviously added to the conductors, but also the icing that happens around the conductors changes the aerodynamic coefficients of the conductor, increases the safe surface that the conductor, projected surface that conductor has. Basically, the wind experiences a larger surface and as such exposes more load on the tower, and that's why the likelihood of failure under wind and ice increases. So we created a joint distribution of wind and ice. We generated basically marginal probability distribution for mean hourly wind speeds using Weibull distributions. We developed the probability distributions for ice thickness using Pareto distributions, and then we used the Clayton-Coppola formulation to kind of combine them, and based on that generated these fragility surfaces that now characterize the probability of failure of our transmission line components, obviously, and also we have one for the system under combination of wind and ice here. One of the x-axis is wind speed, the y-axis is ice thickness, and so one can use this as a database to kind of extract the probabilities of failure of each one of these components. Now, this obviously doesn't apply in a hurricane season, but is if one generates a wind field for potential winter storms, would be very useful in that context. And again, this work is another work that has been published. Saransh worked on that. And now, one of the other aspects that happens after we develop the fragility functions for single towers and develop the probability of failure of single towers is that if you think about it, when a tower fails, conductor tension is basically transferred to the neighboring towers, because this is a tension system. In transmission lines, all the conductors are pre-stressed, and in such, when we lose one conductor, there's very likelihood that we have imbalance of load, and that imbalance of load can cause progressive physical collapse or domino effect collapses that we see a lot within the transmission line systems. Now, one way of characterizing this is through development of analytical models, which is very time consuming and not apply in the large different cases. And you can you should go really in a case-by-case basis. The other way is that we came up with this basically, I want to say, probabilistic mathematical models that characterize the probability of cascade, physical cascade within a system. And then the idea is that some of the towers initially fail due to the wind conditions, and looking into the fragility functions of the specific tower that we have developed. And then some of the towers, neighboring towers, may fail because of that failure, and some may not. And our goal is to be able to do enough perturbations within the simulation to figure out where this continuous failure within the neighboring towers basically ceases. Okay, so again, that is another work that was done. So we are creating this probability generating functions. For example, I is an indicator function. Your hat S is kind of set of perturbations permutations of S initially failed tower and N minus initially not tower, and the towers. And the idea is that you end up with a block of towers that are between the failed towers and generate the probability across that segment of the line. So we actually use this within our model to be closer to reality of what physically happens. So the idea is that if you consider, if you remember, we had these realizations of exposure to wind to our network, and I take the one middle top, and then I can go in. I have information about wind speed and theta, or the direction of the wind at the location of each tower. Based on that, I can go into the fragility function that I have for the towers. I can find the probability of failure. Based on that, I will find the probability of the tower failure, and this is individual tower failure. And then using this cascade model, I can come up with probability of physical cascade failure within each line. Here I'm showing the probability of more than one tower failure probability, more than 5 tower failure probability, and more than 10 tower failure probability within one segment of line. So that can be calculated. So one can imagine that even though the probability of single towers in the top right figure are pretty low, when you look into the potential for cascade and those potential failure probabilities initiating more domino effect failures, it can increase tremendously within a system. And again, that would be probably closer to reality. Now, so with that, you can come up what fails and what not fails. And most of studies that look into kind of connecting structural vulnerability to system level kind of stop there. Okay, and here we kind of go one step after that. And the idea is that what if we implement these probabilities of failures that we have developed for different segments of our system into a power outage model? And that's what this slide is kind of focused on. So we start with the initial outages. We run our DC power model within the system. We define line capacities, and the reason for that is that if, for instance, because of the physical failure, a line fails, the load will be picked up by the neighboring lines. Redistribution will happen within the power system, especially if it is well designed. And obviously that power system is going to overload. And so with that overload comes operational or power cascade, which is different from the physical cascade. So a couple of things that you are seeing here on the top left is one realization, just looking into a single realization output. It shows basically how system performance degrades across this cascade, its stages. We can see that obviously this drop is nonlinear. We can see that some large drops can happen early in the cascade process, and small number of cascade steps can produce a disproportionate loss of service. So, this is kind of my network realization. It kind of shows how the initial outages, which are the red lines, trigger secondary cascade outages, which are the blue lines. And so again, kind of highlighting that power cascade that could happen because of the physical cascade that was happening in the system. On the right-hand side of this, we have system level risk across the more than 1,000 realizations that we had. So this just basically gives you a probabilistic view of this retained service. And taken together, these results show that system impact is not only driven by initial outages, but also by secondary outages, highlighting the impact of power cascade within the system. Now, And also, what this really shows is that it's why it is important that we consider restoration in this whole context, and we also, when we are planning for restoration, we have to look into the impacts more than what really has failed, because two storms with similar initial outages could entirely result in different cascade patterns within the system. And so that needs to be accounted for. So with that, we're grabbing all these outage models that are coming from our power model, and then entering it into making a decision as to how to go about, now that things have failed, how do we go about restoration, or how a utility would handle restoration here. So this is, by the way, this is some work, ongoing work that my wonderful PhD student Puriya Mazaheri is working on. It's not yet published, so you're kind of seeing it fresh out of the oven, but a lot of work that he put into developing this. So one thing you have to notice is that the restoration is inherently, in a sense, discrete. It's dependent on time. Yeah, and this is also resource constraint. We don't have all the resources to put into restoration. So decisions like, for example, when to start a restoration, how long it will run, how many crews are allocated, are very binary and and they happen over time. Okay, at the end of the day, though, our objective here is to minimize the outage duration, and this minimization, actually, this objective is quite linear in a sense, and directly tied to the system impact. So, in other words, it's a very good multilinear integer programming problem that one can use. So. This is basically results from this MILP approach that, or programming that Puriya developed for the system. Left figure shows the repair schedule, shows the restoration is not, sequential, it is parallel, and it is prioritized, and obviously the crew constraints are going to derive that. On the top side of this graph, what you are seeing, in a sense, is the physical state or the repair schedule, the physical versus functional recovery, and this highlights a critical distinction between physical repair that doesn't necessarily transfer or translate to system recovery. So, for example, the purple line here, hopefully it shows correctly there, is the physical outages. You can see that it's decreasing steadily. And the green one is the power loss. And you can see that it drops faster early and then more irregularly. And so reality is that the green line drops faster because it kind of represents the functional recovery, which can potentially happen before physical recovery. And that's because if the system or the network has enough self-healing, in a sense, mechanisms established with that. If there's opportunity for the network to reconfigure or have, power distribution, kind of island generation and whatnot, that could happen. In the bottom right figure, we have the functional versus restoration curves. Again, we are comparing these two early on. You can see that, again, functional recovery is faster than physical recovery for the same reasons that we discussed. And then it kind of lags behind because it's really dependent on the physical recovery to happen before functional recovery happens. So right at the beginning, all the capacity of the system to redistribute and self-heal and everything has happened. And after that, it's really dependent on those physical recoveries. Now, if you do this, this was only for one realization. If you do this over multiple realizations, you're going to have a very similar graph to what I showed at the beginning, which shows kind of the nature of this network and how it's kind of recovers from the system. Obviously, this is only under one investment scenario. This is where a utility can start thinking about, what if I invest more? What if I have more crew members? What if I ask for my neighboring states to come and help, and so on and so forth? And with all of that, one can increase or decrease the speed of recovery here. So really, with the development of this kind of a pipeline from hazard to restoration, we have developed the simulation backbone, that kind of black box, in a sense, that one utility authority can take on and run for their system under different scenarios, either in the form of real time, such that it provides situational awareness into their vulnerabilities, or for long-term planning, running potential different kind of extreme event scenarios and seeing what is happening with their system. And this kind of initiated us towards our path for tech transfer to utilities. We have established a very nice life cycle where we're basically talking with different utilities, in a sense. Am I going over time? Maybe I should speed up, huh? All right. So we're talking with different utilities as our stakeholders as to what their needs are. We also are not forgetting about who's going to benefit from more resilience, which is the communities, the users of this system that rely on this system. So we do have been conducting very organized in-person interviews and also focus group meetings with customers as to what they need for their systems. We have a very close collaboration with the National Rural Electric Cooperative Association, and also with Lawrence Berkeley Lab for development and updating of their ICE calculator for the impacts of outages. And just quickly, I'm going to show you, hopefully this works or not. It's a video of our tool. Basically, this tool can be used. We have loaded it with the pre-event. This event is the ratio of 2020, but this tool can take the loads, the event from National Weather Service, any type of forecasting service, look into the potential vulnerabilities, and notify the utility to start making orders, for instance, for the pieces and parts that they need, or placement of the crew and whatnot. So it can also be used as a real-time tool. So what we've done here, we have shown that extreme events are obviously increasing, and are major drivers for power system resiliency. We have developed very meticulous models, both at the experimental and also numerical side, to characterize the vulnerability of transmission towers, integrated within a power model, so that we can actually model outage models within the system, and used well-known techniques to basically able to restore these outages. At the end, I really would like to thank our funders. National Science Foundation started this project really about 11, 12 years ago, when they funded me with the career award on this topic. And then more projects on different aspects of this came through. NSF Bioenergy Center has been a great supporter with our local work. And in all of these simulations, we have used a lot of work, a lot of facilities, the NARI Evolving Facility, the SIM Center, and Texas Advanced Computing Center. And none of these slides would have come together without my students and our power resilience group, especially Puri and Saransh, did a heavy lifting in helping me prepare these slides and showing the results, and also my other students that are working on different topics. And I'm sorry that I probably starting at 12:15 kind of threw me off. I couldn't look into my time, and deduce as to how much time I have. But anyhow, I'm open for questions. I've put my email here. I know that we have a large online presence, and I really invite everyone, if you have any questions, please reach out to me. And also, if you check my website, it's pretty updated. You can see the papers that we published in this field and kind of look into the details even more. Thank you very much for your attention.
Thanks again, Rob. Maybe insightful presentation. We have time for questions, 5 to 6 minutes. We had about 150 participants in person and on Zoom. With this, we can go back and forth between in person and online questions. So we can start with Omaha.
Yes. Thank you for the presentation. Very insightful. I have a question regarding this system level fragility here shown in slide 23. So I was wondering, how do you convert the component level fragility to system level fragility curves? Maybe this way. Yes,
this one.
Yes.
So there are different methods you can use. You can use couple-based methods. Here, what we use a series approach for assessment of the probabilities. Our goal was that if one of those components fails, it's going to result in failure. But since then we have developed more detailed models as well. You will see them coming up soon.
And online, so I see participants saying hello from Puerto Rico, Atlanta. There is one on congratulating you for promotion to become full professor. Let's congratulate Dr. Alipour. There is one big question by Dr. Ross Porotis. On slide 3, he says it's fascinating. Are those costs discounted to a common basis?
The slide 3. Yes, absolutely.
Yes.
Yeah.
Perfect. So there was a question on if this slide is going to be shared. I mentioned we are recording the presentation. So if you receive the permission, so we are going to make the recording available on ASC EMI Objective Resilience Committee website and also on Durham School YouTube channel. So there is another question on, it would be very interesting to see this type of investigation in Caribbean region.
Sure. Yeah.
Of course.
Absolutely. Let's collaborate. If you are at the capacity to collaborate, we would love to do that.
Awesome. Question from.
Can I ask a question here?
Yes.
Actually, excellent presentation. I think I understood it.
Oh, okay.
Good.
Excellent. That's great.
I'm surprised that hurricanes are that expensive, $1.5 trillion. And do they include tornadoes or just hurricanes?
These are only hurricanes, and severe storms is what includes the tornadoes in this graph. But hurricanes are by itself. But as I mentioned, one of the major reasons is that they're hitting high population zones. It's more of an issue of assets that are exposed at that location. So in coastal regions, we have these large communities that have formed, and with that comes more built environment, more assets that could be damaged, in addition to increasing intensity.
Can I sneak in one more question? You consider only metal towers, you do not consider any other materials, right?
So this study that I showed are lattice type steel towers, high voltage transmission towers. However, the tool that I showed you is actually developed for power grid distribution lines, and we actually have developed fragility functions across all ages and types and exposure levels of wooden poles. That's a work that my student Munir Kudaysar did, and that's available. And based on that, with the same pipeline, we generated the tool that I showed you.
Thank you. So we can take one more question online, and then we need to wrap up on time. So beyond ice, was there or will be also an evaluation of like haboobs, like dust storms impacts?
I wouldn't say dust storms, but my students, both Puria and Muhammad, are collaborating on a paper actually right now, and the results of impacts of tornado on transmission lines. And at Iowa State University, we have a tornado simulator, and we are actually a site for design of the national level tornado simulator, the new RITE facilities. And one of the things that came out of that was to generate fragility functions for transmission lines under tornadoes. Very interesting study. Yeah.
Awesome. Okay, great.
Continue, but we should just allow, if people need to leave, they are welcome to leave.
Yes,
But we could take 5 more minutes if you.
Our director, Dr. Wang, suggests, so we can take a few more minutes if you would like to stay online and in person, so we can.
No pressure.
Yes, there are really interesting questions. So there is one on, would the single tower failure probability changes with the inclusion of microburst probability?
So microbursts are a little bit different in terms of their, in a sense, genesis and a type of loading that they implement on the structure. Probably a little bit closer into two tornadoes, but again, not really the same. So I don't want my wind engineering colleagues to come and to question me here. But it's a little bit a different procedure. But however, numerically and mathematically, and also within the simulation, in our simulators, we can create microbursts and develop fragility functions for them. In fact, a few years ago, we developed vulnerability functions for a suspension bridge under microbursts, and use the same thing. So same idea could apply here. My student Jonathan Martin developed that study.
Another question, thanks, by Professor Korotis. Why are the green lines in slide 31 non-monotonic?
Non-monotonic, okay. So green lines are kind of showing functional recovery. They are dependent on power network recovery, so it's power related. At the beginning, you can see that it's very fast because that self-healing nature of the network comes into place, and so that helps with kind of decrease having the functional recovery immediately. In the next stages, it's dependent on the physical repairs to the system to happen. After enough physical systems within a branch happens so that that branch can be reloaded, then the recovery happens. So that's why it's kind of stepwise. I hope that answers the question.
So it seems like there is some trouble to hearing my question, so I'm going to get closer. The next question is by Professor Jay Pockets. A number of questions. So the first one is, what is the typical percentage of load from wind online versus structures? On lines versus structures. So what is the typical percent of load from wind online?
On the conductors versus
structures, yes.
That's a very good question. I can say that on the conductors, it's much higher than what is on the tower. But I'm sorry, Jay, I do not have the numbers like top of my head as to what the percentage is. But lines, if you imagine, we have about, for example, on a priory type kind of land topography, at about every 1,000 feet, there is a transmission tower. So you can think about exposure of 1,000 feet of conductor to wind versus the kind of point tower exposure that we have. Doesn't mean that the tower is not exposed, it's just that a lot of load is being transferred from the conductors.
And we have changed it. I mean, now that questions are open, we have allowed the online people to unmute and put their video on. So Dr. Puckett, if you prefer to do that, as you say, it's totally fine.
Yes, like if there are like more questions.
Yeah, feel free.
Okay.
Yeah, good presentation. Thank you, Alice. My question there is, what's really the important element there, the line or the tower? Related, a lot of pole structures are used for transmission too, and steel, the toughness of those is much different than that of a tower. So in your modeling, did you include towers and or not, or poles. I'm sorry.
So the fragility functions that I developed and the analytical models that I showed here are for lattice type transmission towers. Specifically, I showed the data for a 500 kV tower is what I showed. So it's pretty major tower in terms of size and capacity. It's very different from our poles that are these tiny wooden structures, with a even shorter height and whatnot. So and in context are different, yes. But we've done the work for both of them.
Oh yeah, but there's still transmission structures, so I'm not talking about distribution structures.
Oh, you're not talking about distribution. Yes, absolutely. We have those as well, but we haven't modeled them here. No.
Okay. So I was just wondering then how robust your models are. What's the percent of poles versus towers for distribution? Because there's, at least in the West, there's lots of poles out there.
That's true. We can see that depending on the voltage, we can see that the structure types are different. So I really haven't done a study as to what is the percentage of poles, for example, the steel tube-like poles versus lattice type transmission towers. But what I can say is that this network that we modeled had lattice type transmission towers.
Okay. All right. And then break structures. How did you model break structures?
Break structures, we didn't necessarily model. We have modeled conductors and insulators, and that's about it.
So wouldn't that break structures would significantly affect your cascading model, wouldn't it?
And are you talking about the end towers? Is that what that means?
Yeah. So they, as I understand it, the break structures are every so often they are designed for the cascading failures, which will limit the exposure. So that would have to be included in the model.
Absolutely. Yes, absolutely. Our cascade model is defined as towers between break structures. We call them end structures. That's why I for a minute I kind of was frazzled there. But yes, the cascade models basically stops at the end structure because that's exactly the purpose of the end structures. But in between, the segments can go down because of the physical cascade. So yes, we have modeled them, and our assumption in modeling was that they would never fade. Although that's not necessarily true, but that's kind of the assumption that we made.
I see. Good. All right. One final question. Did you model the boundary layers at all?
Boundary layer of?
The boundary layer?
Wind?
The boundary layer effects? I know your wall of wind was uniform flow, but did you model the boundary layer?
In our wind field generation, it is included, and that's pretty much it.
Okay. Thank you.
I just want to add to what Dr. Pumpkin is saying. Actually, poles are probably going to be more in the future than lattice towers. Lattice towers are very, very expensive.
Absolutely.
To produce, to make. So that's kind of industry of the past. So maybe in the future there will be more emphasis on having that single pole. It doesn't have to be wood; it can be steel.
Steel or concrete or fiber. Yes, absolutely. That's a true statement. It's just that that's the data we have developed, and our network happened to have lattice towers, so that's why we use that. So everything really matched nicely in this context. But the fragility framework, function development framework that we have is entirely implementable on any type of pole. As for example, we have implemented also on wooden poles, which are more, in a sense, flimsy, if you think. And also our pipeline within the network level resilience assessment stays the same.
Just one related comment. Our experience with directly embedded towers, the toughness of those is just incredible. I think you'd have a hard time failing them if you planned your failure mode in the foundation. I mean, they might lean over a little bit, but they'll absorb a whole lot of energy.
That would be wonderful. That's what we're looking for. It may put me out of business, but it will be good for the community.
Awesome. Thanks, Professor Todros, Professor.
I don't want to take too much time here,
Yes,
but
go ahead.
I would love to know about this tornado simulation lab that you have at Iowa State.
Yeah.
What is it and how elaborate is it? And can we have one here in Nebraska?
One of the
You can use the one that we have in Iowa. So we currently have a tornado simulator, and I should really know the size because I've been working on this project forever, but I probably cannot have justice about it, so I'm going to leave it out. But it is currently in our Department of Aerospace Engineering, and open to use. We are open to collaboration.
I'd love to go and see it one time.
Please come, and we'll love to give you a tour of the facility. We actually, these transmission towers, we have also tested it in our tornado simulation. One of the results that I showed was the kind of the initial data that we used for that kind of tornado simulation within the transmission line. But at the same time, as I mentioned, we have this NEORITE facility, which is hopefully that in future is going to be an experimental facility within the NERI network, which we will have a much larger tornado simulator where some of the structures of a smaller footprint can actually be tested to in that at full scale, basically. Yeah.
Awesome. We can wrap up here.
Lincoln would like to ask one question if we can have in Lincoln.
Oh, Lincoln, is there a question?
Oh yeah. Hi, Dr. Alipour. Thank you so much for the presentation. I'm Yunping Liang. I'm an assistant professor at Durham School, and I'm on the Lincoln campus. I do have a question. Actually, that's more like a discussion, not real question. So my understanding is like I know you did the community engagement to get the insights from the actual resident and business owner. But my question is like down the road, or have you ever got the chance to explicitly involve these socioeconomic factors in your model or decision-making tools? So for instance, just one example, sometimes when the community, they no matter plan for resilience enhancement or the emergency management, they are subject, their hands are tied, right? There are a lot of constraints. So it's not like they don't want to do, they just, because a lot of factors. So yeah, that's my question.
Yes, for at the distribution, the projects that we have for the distribution line, we have engaged the communities, and we are developing. My colleagues, I work with colleagues in social sciences at Iowa State University, and we are developing basically social vulnerability indices that represent the impact of elongated outages. And one of the reasons we're running all these surveys and also running these interviews with the community members is to understand what are the impacts of these elongated outages on the community. And that when we are planning for our outage restoration, that can become a factor within that decision making. It can also come up as a factor within mitigation planning to ensure that some of the communities that are more on the disadvantaged side are less impacted by these type of events. So certainly it is something that we have our eyes on. We're just at the stage of collection of data. However, our models are capable of integrating different kind of resilience metrics, and one of them can be social vulnerability or impact of these longer outages of the communities.
And how would you envision the newly developed vulnerability index distinguished from the existing one developed by CDC?
So really, it really depends. These kind of the weighing of different parameters really becomes a decision parameter. This becomes options for example, utility owners to decide as to which parameter they want to kind of drive their decisions on. And our job is mostly to kind of characterize them and implement a pathway for them to be included. But then, for example, one of the things that you can think about is, for example, undergrounding grids is very expensive initially. It's a lot of ratepayers, increase in ratepayers rates, customers' rates at the initial stage, but huge return on investment if, for example, if the location is really prone to winds. But sometimes our goal is with these tools, utilities can present and justify that to the ratepayers as to, these are the impacts you could have by implementing this type of, for example, asset hardening or mitigation compared to the other ones. It can also, as I mentioned, provide situational awareness if we understand what are the vulnerabilities within the community. If an event is happening and the utility, through these models, the simulation package can see where the damages are happening and whether these socially vulnerable groups are being impacted, they can allocate the resources there. So it really becomes a very useful tool for decision making with different parameters that could be weighed in different ways. And it can be a great tool for utilities to be able to communicate risks with the ratepayers, justify potential investments, and kind of drive the decision at the community scale, in a sense, and integrate the community within that decision making.
Thank you.
Thanks so much, everyone, for this great, engaging discussions. Of course, thank you so much for this excellent presentation and very insightful. I really appreciate the support by ASC, EMI, Objective Resilience Committee, and also Durham School to sponsor this visit. So in the afternoon, we are going to have Dr. Alipour to visit our city campus in Lincoln. So we are going to have a tour of Qubit Hall, meet with our faculty in Lincoln. And with this, we can wrap up. Thanks so much, everyone, for joining us in Omaha, in Lincoln, and also in Lincoln.
Good job.
Thank you.
Thanks for joining, everyone.